Welcome to the Overdose. In this lecture, we're going to talk about membrane potential. Okay, in the last video, we talked about the Gibbs-Donnan equilibrium, and I talked about it with respect to the blood plasma to the interstitial fluid. And what I'd like to do now is talk about it with respect to the cell and the interstitial fluid. So here I'm drawing my cell, and inside the cell, I have proteins which contain several negative charges. And I have potassiums that have several positive charges. And so right now, the inside of the cell is neutral in charge. The outside of the cell is also neutral in charge. So I have initially a few potassiums start to move out because of the concentration gradient. And what I get at the end of this is the inside of the cell is -2, the outside of the cell is +2, giving me a total charge difference of -4. And then, because of the concentration gradient, a few more potassiums will move out. And what happens here is I have an inside charge of -4, an outside charge of +4, a total charge of -8. At the same time, I would have had diffusion, and the diffusion would have started out as having a total of 16 potassiums in the cell and 0 outside the cell. But then after the first 2 moved out, I had 14 in and 12 out, and then 2 more moved out, and I had 12 in and 4 out. So you can see I'm getting a work from my concentration gradient. I'm getting work moving out of the cell, but I'm also getting work from my electrical gradient, work moving into the cell. When these become equal, the fusion will stop. And this is an interesting place where the work of the electrical energy is equal to the work of the concentration energy. This is an equilibrium. And so when we're at equilibrium, being an interesting place, we want to know what these numbers are. What is the work I can get from the electrical field? What is the work I can get from the ion gradient? And let's go back and review the ideal gas law. Remember that P times V is equal to nRT. And what is P? P pressure, is the same thing as saying force over meters squared. And V, what is that? That is equal to meters cubed. So when I multiply force over meters squared times meters cubed, I'm left with force times meters, or you would say force times distance, which is equal to work. So in this ideal gas law, I'm asking what is the work that I get from a certain amount of gas. You'll remember that work is equal to the kinetic energy change plus the potential energy change. And so whenever everything stops moving, the kinetic energy is equal to 0, and the work is equal to the change in potential energy. And so here, because there is no movement, force times distance seems like a misnomer. However, we can rewrite this that the potential energy is equal to the moles times the gas law constant times the temperature times the natural log of the concentration in one area divided by the concentration in the second area. And so this is the work done by a concentration gradient. And so what's the work done by the electrical gradient? We can answer that question. Again, work is equal to the kinetic energy change plus the potential energy change. When we're at equilibrium, the kinetic energy change is equal to 0, and so the work is all due to the change in potential energy. And you may remember from physics class that the change in potential energy due to an electric charge is equal to negative of that charge times the electric field times delta X. We'll examine the electric field really quick. The electric field is equal to the force divided by the charge. And so you'll see that if we were to put this into the equation, we would have negative Q times force over Q times delta X. And whenever we cancel these out, we get, again, force times delta X, which force times distance is equal to work. So this seems to make sense. Also remember that E, or the electric field, times delta X, this is our definition of voltage. So V equals E times delta X. And we don't usually use the term voltage. It's usually the word potential difference, or delta V. And so we can rewrite this as the change in potential energy is equal to negative of the charge times the voltage, or the potential difference. And creating a little bit more space, we'll say, what is this charge? Well, I have a certain number of moles of positive charge. Faraday, he created this number called Faraday's constant, which says, what is the total charge I would get from 1 mole of electrons. This also works for protons, so I can answer the question, what is the charge I would get from 1 mole of protons? So the mole of potassium times Faraday's constant. But you have to remember we have some ions that have more than a +1 charge. For example, calcium has a 2+ charge, so we need to multiply this number by Z, Z being the charge per ion. So we get that Q is equal to NFZ, and we can replace that and say that the potential energy, or the work, at equilibrium is equal to V times NFZ. The potential energy, or the work, is equal to V, the potential difference, or voltage, times NFZ, which is the moles of charge, Faraday's constant, and the charge per ion. Now here's the point of all this. We have this really fancy equation called the Nernst Equation, and basically what it's saying is whenever these are at equilibrium, the work being done by both are at equilibrium. So I can say that the voltage times NFZ is equal to nRT times the natural log of the concentration in one area divided by the concentration in a second area. Now I have N in both of these places, so that will cancel out. Then I can divide both sides by Faraday's constant times the charge, and I can get that the voltage is equal to RT over ZF times the natural log of the concentration gradient. Now you'll remember, or you'll notice rather, that in biology, people like to use the letter E instead of V, and E representing the potential difference. The reason I chose to use V in this example is because E in physics represents the electrical field. So we say that E is equal to RT over ZF times the natural log of the concentration gradient. This is known as the Nernst equation. The Nernst equation has a couple of implications. The first of all, whenever the equation is being used, you have to say that in this situation, all the forces will be equal. If the forces of, or the work of the concentration gradient is not equal to the work of the electric gradient, this equation doesn't apply. Second of all, we can ask the question, if my ion gradient is a certain concentration inside and a certain concentration outside, then what will the voltage be if that is at equilibrium? When I ask the question in this way, we call it the equilibrium potential. I can also ask this in another way. I can say if my potential voltage is a certain value, what must my concentration gradient be? And when I ask it this way, we call it the reversal potential. What I'm saying with C is I have a cell and I insert an electrode here and I insert an electrode out here and I apply a certain voltage, and then the potassiums can either be shot out of the cell or they can be shot back into the cell depending on what that voltage is. So whenever those potassiums come to equilibrium, what would their concentration be? And we call that the reverse potential because we can reverse the concentration of potassium by changing the voltage across the cell membrane. Now let's look a little bit closer at the math and see if we can do a little bit more manipulation. We can say that E is equal to, and now I want to point out that whenever we were talking about the potential energy from the electric field, we said that the potential energy had a negative Q. And whenever I replaced that, I didn't leave the negative in there. And I'm going to go back and try to explain that. So we said that this is equal to delta V times ZFN. And so we got to put a negative here. So when we go back to the Nernst equation, recall that I said that in the biology, or in the Nernst equation, we like to use the letter E instead of V. So we'll say that E equals negative of the RT over ZF times the natural log of the concentration gradient. Now naturally, the concentration gradient is going to be where the top of that fraction is going to be where we have a high concentration, and the bottom is going to be where we have a low concentration. Now, if you remember that the negative of some log is equal to the inverse of the positive log. So now let's get rid of the natural log and turn it into a log base 10. Why? Because nobody likes working with natural logs. And you'll remember that because the natural log is really log to the base e, where e is Euler's number, we can convert that to log base 10 with the following format. So log base 10 of the concentration gradient divided by log base 10 of Euler's number. Now log base 10 of Euler's number is equal to approximately 0.434. And since we're dividing by 0.434, that's the same as multiplying by 2.3, or the inverse. So when I take 2.3 times RT over F, Faraday's constant, I get 2.3 times 0.082 times, now at 37 degrees Celsius, we're at 310 Kelvin, 310, divided by 96,487,000 for Faraday's constant, and you'll get roughly 0.0006 ... We can convert this and just call it 60 to 61.5 millivolts. Now we can make that a constant because we're talking about inside the body, so the temperature shouldn't vary. So we can say that 60, depending on what book you have, it'll either be 60 or 61.5 or some number in between that, divided by Z. So divided by Z times the log of the concentration gradient. Now some textbooks will try to get rid of Z in that as well. That's a bad idea because, as you remember, we can have a positive or a negative charge. So if you're talking about chloride ion, Z is equal to -1. And if you're talking about calcium, then Z is equal to +2. And now I just want to point out that if you have some number with a decimal in it, it's probably a little bit more accurate. But going with 60 is relatively easier to remember, and it's easier to do math with. So let's look at what the concentration gradients are inside and outside of the cell. So I'm going to look at the concentration in the cell. For sodium, it's 150 millimoles, and outside of the cell, it's 15 millimolar. Potassium, inside the cell, outside the cell is 5.5. Chloride ion. So now what is the log base 10 of the out over the in? So we'll start with sodium, and log base 10 is 1. So we're doing 150 over 15 is equal to 10. Log base 10 of 10 equals 1. Potassium and chloride. So this is the log base 10 of the outside concentration over the inside concentration. Now you remember this 60 divided by Z times the log. Now if Z is negative, that means we can multiply and get a negative log. When we do that, we take the inverse. So for chloride ion, that would change this to -1.14. So by asking the question, should we use as our constant 60 or 61.5, I went ahead and laid this out. If our log section of the equation gives us these numbers, what would we calculate the membrane potential at if we use 60 or if we use 61.5? So for sodium, we would have a membrane potential either of 60 or 61.5. With potassium between 86 and 88. With chloride between 68 and 70. And so what do the books typically say? The books will typically say sodium's equilibrium potential is +60, potassium's is -90, and chloride's is -70. So the bottom line is the potassium and the chloride ion gradients usually come really close to the Gibbs-Donnan equilibrium, what you would expect from that theory. So what this typically means is that the theory almost explains the potassium and chloride ion concentrations. Sodium, on the other hand, is not adequately explained by the Gibbs-Donnan equilibrium constant. For example, we have a high concentration gradient driving sodium into the cell. So if we call this out and this in, sodium's concentration gradient is driving it in. Furthermore, the resting potential of the cell is usually between -70 and -80. That means that the electric gradient is also driving sodium in. And so when we have a cell in the situation we just described, the negative ions will line up across the membrane and the positive ions will line up outside the membrane. And anyone who's had physics will realize that now that I have a positive and a negative charge separated by a very small space, my membrane has just become a capacitor. And so we see that different cell types maintain different potassium concentrations, and because of that, they're going to have different equilibrium potentials. When we're looking at and studying equilibrium potentials, most of the time we're looking at or studying neurons or myocytes, because these cell types have the special ability to be able to fluctuate their potential or voltage up and down in order to either relay messages or cause work to be done. So that brings us to our next point. No ions are ever at their exact equilibrium potential. So the place where we find a cell while it's resting, that's called the resting membrane potential. And every cell type is going to have a slightly different resting membrane potential, but most of the time this is studied in excitable cells such as neurons and muscle cells. And so we usually will find a neuron or a myocyte with a resting potential between -70 and -80 millivolts. This is near the potassium and the chloride concentration gradient equilibrium potential. That's because the cell is very permeable to potassium, but it's not very permeable to sodium. These ions can easily move across the membrane toward their equilibrium. So this means that the Gibbs-Donnan hypothesis can mostly explain these two ions. However, sodium is not near where we would expect to find it, with the Gibbs-Donnan hypothesis being the explanation. So we can say sodium has a high concentration driving it into the cell. It has a high electric gradient driving it into the cell. And this means we can make two conclusions about it. The first, we can conclude that it is not explained by the Gibbs-Donnan equilibrium. And we can also say that the sodium concentration gradient is only explainable by the sodium-potassium ATPase and its low permeability. Low sodium permeability only means when the cell is at rest. Let's talk more about the sodium-potassium ATPase, because I think this is a point where most of the textbooks either are inadequate or they get it completely wrong. So here I have my cell, and I have, in this case, 2 potassium outside and 3 sodium inside. And so what the sodium-potassium ATPase does is it will take these 2 potassium, it'll take these 3 sodium, it'll cause them to switch places. So the sodium gets shipped out, the potassium gets shipped back in. But you will ask the question, why doesn't the sodium-potassium ATPase explain the potassium concentration? That's because the potassium, if more gets pumped in, it can easily just move straight back out. And so as 2 potassium get pumped in, 2 potassium move out to keep the potassium concentration where it's at, created by the Gibbs-Donnan equilibrium. But on the other hand, when 3 sodium get pumped out, the sodium is stuck out here. It cannot move very easily across this membrane, so the permeability being low means that the sodium-potassium ATPase can explain the sodium concentration. The second thing is that the sodium-potassium ATPase is said to be electrogenic, but when people say it's electrogenic, it has nothing to do with where it maintains the sodium concentration. What it means when it says it's electrogenic is, let's say that we have the 3 sodium on the inside again. On the outside we have 2 potassium and 1 sodium. At this point, the membrane is neutral. There's 3 positives outside and 3 positives inside, so the charge difference is 0 among these 2 sides. But these 3 sodium will get pushed out. These 2 potassium will get pushed back in. And so when it's all said and done, I will have 4 positive charges on the outside and 2 positive charges on the inside, creating a charge difference. That means more sodium gets pumped out, or more positive charge gets pumped out than the positive charge that gets put back in. So this 3:2 ratio that we get from here, this adds about 4 to 6 millivolts to the membrane potential. So let's look at what we would have if we killed the sodium-potassium ATPase pump. So let's say that resting potential is at negative 70 millivolts, and that sodium's equilibrium potential is somewhere around positive 60. And then we'll say that 0 is right here. And we maintain a membrane potential right here. And then the second we kill the sodium-potassium ATPase pumps, we come up here to negative 66. So immediate jump up to negative 66, and then there's a slow, gradual slope up to 0. So eventually, if you were to stop all the pumping action in the cell, sodium would be able to move in, and potassium, because sodium moves in, the increased positive charge would allow potassium to come on out, and with the sodium moving in, the potassium moving out, eventually a new equilibrium potential, new resting potential would be found at 0. So this initial jump right here from negative 70 up to negative 66, this is due to the 3:2 ratio of pumping out positive charge. That is what is meant by the pump being electrogenic. The slope that we get afterwards, that is due to the sodium finding a new equilibrium, and potassium therefore also finding a new equilibrium because the ATPase is what's responsible for the sodium gradient. So let's ask another question that I think most of the textbooks inadequately explain. The question is to say, to go from 0 to negative 70 millivolts, how many potassium ions have to move? The textbooks are going to say, not very much potassium has to move. That's not true. The truth is the potassium concentration doesn't change very much, but lots of potassium actually moves. And we can actually quantify how much. So we'll treat the cell membrane like a capacitor, just like I showed you. And so we say that the cell is approximately a capacitor. In other words, if I draw my cell, I have a bunch of negative charges that line up along the membrane, and then I have a bunch of positive charges that line up on the other side of the membrane. And this is a capacitor. So the membrane capacitance is roughly 1 microfarad per centimeter squared. So in order to see how many potassium ions have to move, we need to figure out what the surface area of a cell is, and we need to figure out how to relate capacitance to voltage. If we assume that an average cell is spherical and about 50 microns in diameter, converting to centimeters will get us a cell that's approximately 7.85 times 10 to the negative 5th centimeters squared. By converting microfarads to farads and dividing it by the centimeters squared, we can find that the charge on a membrane capacitor is approximately 7.8 times 10 to the negative 11th farads. Now remember, we can define capacitance as equal to the charge divided by the voltage, or the charge divided by the potential difference. Well, we don't know what the charge is. We do know what the capacitance and the potential difference are. So we can say the charge is equal to the potential difference times the capacitance, which is 70 times 10 to the negative 3rd millivolts for the potential difference, and 7.8 times 10 to the negative 11th for the capacitance. And so we're going to get a charge of 5.46 times 10 to the negative 12th coulombs. And if you remember back to your physics textbooks, the milk and oil drop experiment, we determined that the charge on a single charge, whether that's a proton or an electron, is approximately 1.602 times 10 to the negative 19th coulombs. So now we can ask ourselves, what is the potassium concentration needed to change to get to 5.46 times 10 to the negative 12th coulombs? It would take about 34 million potassium ions moving to create the capacitance that we see on a biological membrane. 34 million is a lot. That's a big number. So does that outward flux of 34 million potassium ions change our potassium concentration? our concentration is equal to the number of potassium ions we have, in other words, the moles of potassium ions, divided by the volume of the cell, or the liters contained in the cell. So because we have a spherical cell in this idealized world, the volume can be guesstimated or estimated as 4/3 times pi r cubed, r being 25 microns. And we find that the volume of the cell is about 2.6 times 10 to the negative 12 liters. But really what we're looking for, we already know what the concentration is, and now we've figured out what the volume is. We're looking at the number of potassium ions that are in the cell. Let's just say that our intracellular concentration of potassium is 150 millimolar. So we can take that 150, which would be 0.15 molar, and multiply it by the liters. And you'll find from that we have 3.9 times 10 to the negative 13 moles of potassium in the cell. And so by using Avogadro's number, we can convert that 3.9 times 10 to the negative 13 into a number of potassium ions. And you'll see that's roughly 234 billion potassium ions inside of a cell. So the 34 million potassium ions that have to move out of the cell represent not 10%, not 1%, but 0.15% of the total potassium that was inside the cell. The point of all of this is that as these ions create a potential difference, their concentrations do not change much. And so you can see from the text that we are going to be talking about three kinds of potential. There's diffusion potential, equilibrium potential, and resting potential. So far I've explained the equilibrium potential and the resting potential, but the diffusion potential, that is the potential as the ions are in flux. There are four other kinds of potential that are pretty important. These do not have to do exactly with what we're talking about now. For example, there's a threshold potential, an action potential, an excitatory postsynaptic potential, and an inhibitory postsynaptic potential. These all refer to changes that occur at the membrane due to various other things, but they are not exactly what we're talking about now. And we will discuss all of these whenever we get into the neurology and into the cardio and muscle physiology. So diffusion potential, I say there's an electrochemical gradient caused by a selectively permeable membrane. The ion can move down its concentration gradient. Movement of the ion is the fundamental basis of potential, so the magnitude is due to the size of the concentration gradient. When the push of the diffusion gradient is exactly equal to the pull of the charge gradient, this is called equilibrium potential. And right here, when I say requires the movement of only a few ions, you should know that this is only a few million, and that if you really mean few, you're talking about concentration. Here we have the Nernst equation. You can also exchange the E for a V. E seems to fit because we are talking about the equilibrium voltage or potential. R, again, gas law constant, absolute temperature, valence charge, and then we're talking about the concentration gradient. And then this here, right here, the concentration out versus over the concentration in, this is actually a typo in its current form. If we changed it to the log base 10 form, it would be correct, but in the current form, it should be the concentration in over the concentration out. And then when you change it to log base 10, it's because you're multiplying it by a negative. If you were to put a negative 2.3 right here in front of RT, multiplying by that negative causes the logarithm to take an inverse. And again, these first two are typos. This should be in, this should be out, this should be in, this should be out, and then this one is correct because we have multiplied off the negative number. And so right here what I'm doing is I'm just showing you three different ways you can express the Nernst equation for biological membranes whenever the temperature does not fluctuate. And so especially when we're talking about a temperature of 37 degrees Celsius, if we're talking about any other kind of animals, you want to revert back to at least this form of the equation because their body temperature may not be 37. Also, for some strange reason, if you ever have to use this equation on a timed exam, for example, like the MCAT, use 60 because your answer will not change significantly. Furthermore, if you're using this bottom equation, be careful because if you're calculating something that has a negative charge, z would become negative, causing a secondary flip. So we already had one flip from that negative. We'd get a second flip from that negative, and then we would have concentration in over concentration out. The other thing you have to be careful about if you're using the 61.5 equation is if you have a valence of 2. So calcium has a 2 plus valence, so you would have to divide this by 2 to get the same effect as dividing by z. Here I have some, we'll call them rounded concentrations of intracellular and extracellular. So intracellular 15, extracellular 150, and you'll know that the log base 10 of 150 over 15 is equal to 10, so log base 10 of 10 is 1, and when I multiply by my constant of 61.5 or 60, I get 60. You'll also see that I included in this calcium. Intracellular calcium is extremely low. The calcium concentration is mostly sequestered in the endoplasmic reticulum, and so when we're talking about intracellular, we're talking about the cytosolic calcium. The sarcoplasmic reticulum calcium concentration tends to be fairly high. So with the resting membrane potential, we can figure out what the contribution of each ion is by its permeability. So because we are not at the equilibrium potential for any ion, we can say, well, what is the resting potential? And we basically take the equilibrium potential and multiply it by its permeability, and that gives us the resting membrane potential. It's approximately negative 70 to negative 80 for excitable cells. Now, resting membrane potential is altered about 4 to 6 millivolts due to the electrogenicity of the sodium-potassium pump. So multiplying the membrane potential, the equilibrium potential, by the permeability and adding all of those together for each individual ion will get you to almost the resting potential. You have to also account for 4 to 6 millivolts from the pump. Then last but not least, we have the Goldman-Hodgkin-Katz equation, sometimes called the GHK equation, sometimes called the Goldman equation, sometimes called Hodgkin-Katz. Whatever you call it, the GHK, it's basically one of the two ways we can determine the resting membrane potential. And I just alluded to this in the last slide. So we have the first part, this Nernstian part of the equation. And then on the logarithmic portion of the equation, we would take the permeability of potassium times the potassium concentration outside. The permeability of potassium times the potassium concentration on the inside. And it's just like with the Nernst equation, out over in, and then when you have a negatively charged ion, this is a mistake, a typo, a negatively charged ion, you do in over out. And then you have the relative permeability of each ion. Usually what will happen is we'll set the permeability of potassium to equal to 1, and then we'll say that the permeability of sodium is some percent of the permeability of potassium. We'd say 0.01 or something like that. There's another way to determine the resting membrane potential, and that's using the chord conductance equation. This is a little bit more tricky, but it's basically the Nernst equilibrium potential of potassium times the conductance of potassium over the total conductance. The conductance of sodium over the total conductance times the sodium equilibrium potential. You add all of these up, and you can use that instead of using permeability. And so we said that for potassium, we can explain its equilibrium potential mostly from the Gibbs-Donnan equilibrium. We can explain the sodium equilibrium potential from the ion pumps. And so the resting membrane potential would be a contribution of ion pumps, Gibbs-Donnan equilibrium, and the effect that they have called the diffusion potential, which is basically the potential difference that is created by unequal amounts of ions on each side of the membrane.